The last topic in our descriptive statistics segment in this module is to talk about probability plots. And this is just yet another number of techniques that if we would have had really fast computers at the very beginning of these ideas, we may not have ever really developed them, at least maybe not quite in this particular form. Stem and leaf diagrams are probably that type of thing for sure. And here the probability plot is really is a nice aid, a graphical technique for and visualization of the data, particularly if we want to have a quick early kind of view as to whether a particular probability model is appropriate. And in the olden days, you had special paper that had a special vertical scale that you plotted on. And it's a bit like the idea of what you do with log scales. Right? You could plot on a log scale and convert that information over into something that's easy to use on an arithmetic scale, or you can get just the special paper to begin with. Right? Well, nowadays, of course, you just click a different button inside some sort of GUI that does your plotting. Right? For here, let's take a look briefly at the exponential model, and then we're going to go to the normal distribution model. And let's go right to the CDF of the exponential model, that it's equal to 1 minus e to the minus lambda x. Right? The probability that x takes on any one value or less is given to us by this nice simple function here. Of course, the simplicity of that function is exactly one of the reasons that we end up using it so much. Note that we could simplify things here and turn this around a little bit. First off, we're just going to call, instead of this fx, we're just going to call it f to make life a little bit easier here. And we're going to pull some things over. Let's pull f minus 1 equal to minus e to the minus lambda x. We now have probabilities over here, minus 1 is a negative number. We don't really like that very much, so we're going to turn that right on around. And so that's really 1 minus. And then we're going to take the natural log of that. So now we have natural log of 1 minus f is equal to minus lambda times x. And since our cumulative values are always less than 1 minus this number is going to provide, when we take the natural log, a negative number. So we don't like that either, so we're going to put that minus sign right over here. And if we call this whole left-hand side y, then what we have is equation of a straight line. That has an intercept equal to 0 in this particular case, and of course its slope is equal to lambda. And so now we have a kind of interesting thing that has just been developed for us, and that is if we were to plot our data on a special arithmetic scale. So there's our x values, and we're going to plot then minus the natural log of 1 minus f here. That's our y. Okay, so what we're going to do is we're going to get from our data, we'll have all of our different xi values, right? And we'll go compute what the observed CDF is for each one of those, and then we'll convert that, transform that into a y value using this expression here. So we can add a subscript of an I that goes along with each one of those. And then that's what we plot. just throw a couple more data points in here. And note that in this particular example that I put in here, we don't really have a nice straight line. There's a little bit of a curve, and that tells us something right off the bat. Again, on this special vertical scale, that's our probability scale associated with the CDF, that if this was really coming purely out of an exponential model, we should see a nice perfectly straight line, all the data points lining up on that. We rarely ever have that, but the degree to which these points do line up on a straight line tells us something about whether that distribution is a good model for our data. Sometimes what happens is we've already decided this is the distribution we want to use, and now it's, well, what should the parameter be? And that's partly going to be what we're going to focus in on in the next set of lessons. But here, what we can also do is say, you know, look, this lambda is the slope of this line. So we could draw a line through all of the data, and that wasn't a particularly very good one, but there's one estimate of lambda. I'll call it lambda sub I. Or rather, let's call it lambda sub 1. We could say, well, I don't really like that line. That emphasizes too much the lower end of the data. Maybe I'm more interested in the tail data, large CDF type values. In which case now you come along and you fit out here in this region. So that would be a second one. And you can repeat that exercise over and over and over for different areas that you're interested in. If you're interested in the body, well, then maybe you use a linear regression kind of model to fit the data here in the middle portion, that sort of thing. There's a lot of ways you can come about doing it, and it's a very convenient way. And again, in the old days where computing resources were vastly more limited than what we have today, taking the data such as that we might have up here and processing it to create the observed CDF, doing that transformation was not a particularly difficult type of thing. And then you could plot this on the special paper and then graphically come up with your estimate of the parameter that turned out to be of interest. Right? Or perhaps you did this exercise before on a limited portion of the data set to get kind of some sort of sense of whether this was the right direction to go before you invested a great deal of time doing a lot more work. Right? So that's the exponential model. The normal model is done in a similar kind of way, except for there's a few wrinkles that we have to do because of the complexity of the normal model itself. And remember that our CDF for the normal model, well, we don't actually have a closed form answer. It's been numerically evaluated, and it's this capital phi in terms of the standard normal variate z. And so what happens there is that you can do one of two things. Either you can buy the special probability paper, kind of like the special graph paper in the olden days with the log or the semi-log kind of scale, or of course you know it's pretty common these days that you can go into something like Excel or any kind of graphing program, math program, and be able to do log or semi-log kinds of things. And that means your vertical axis is going to be a nonlinear scale, right? And if you looked at the old days of the actual paper, you'd see it this special nonlinear vertical scale for the normal probability paper. And there are certain special high-priced kinds of software out there, such as Minitab, that will give you the push button to do the same kind of thing in a digital sort of fashion. Or what you can do is do an arithmetic scale in terms of z versus our random variable. And that's what we're going to show how to do here for our aluminum cyclic test data. Right? And the reason why this works is that z through our table has, for every unique z value, there's a unique value for the CDF. Right? So plotting z is just a special transformation over here, and we can do this on a arithmetic scale, and if we end up with data that falls roughly in a straight line, then we say, hey, look, this is about a normally distributed random variable. Right, same kind of idea as what we had for that exponential model. And it's pretty convenient and easy to do this kind of transformation, especially say in Excel where you got an inverse normal function and you get the same kind of thing in lots of different packages. Okay, so let's look at how we might do this for our 70 data that's a part of our cyclic test setup. Right, and you're going to see that in my table here I've got 4 different columns. The first one is J, which is just the order of the data from 1 all the way up to the total number, which is 70 in this particular case. And then in the third column I have the actual data points listed from low to high, and I've of course truncated to save space and not show all 70 of them here. Okay. The second column is our observed CDF done in a slightly special kind of way, and then the last column is our standard normal variate that corresponds with our CDF values that we have here. So this is really our observed CDF value. Right, which you'd say, well, all right, the first one, I should take 1 divided by 70, and that should be this number. And that's what you'd see here, the 1 for the J, 70 for the N. The minus 1/2 is a stylistic thing. And I referred to this before when I did a CDF for the histogram, and that option for that particular CDF was to divide by n plus 1 as opposed to n. And that's another approach to this. And again, the reason why we do this is because we recognize that this data set is not the entire population, and particularly for a normal distribution where we recognize that the possible values of x range from negative infinity to positive infinity. Well, we don't ever want to have an observed CDF that's exactly 100%, because that says that, well, we can't have any x values that are larger than that. And we know that that's not theoretically the case. So we could arbitrarily divide by n plus 1. In this case, and of course you just have stuff up here. In this case, the idea is you take j minus 1/2, and so when we get to 70, that'll be 70 minus 0.5, or 69.5 divided by 70, and that gives us the 0.9929. And down here at the lower end, instead of 1 over 70, we end up with a 1/2 divided by 70. The 1/2 value is entirely an arbitrary sort of selection. There's a lot of different approaches, and there's a little bit of style as to how one might go about it. Large data sets, it's really not going to matter which approach that you use. Okay, so what we're then doing is we're simply taking the inverse function of our observed value to give us the ZJ. Okay, so let's take a look at what that would be like if we were going to process this by hand. Back in your appendix of your textbook is where, of course, our standard normal table is located. And we had, for that first one, 0.0071 was our observed cumulative value, right? And that corresponds with a minus 2.45 z value. And that's, of course, where we get this number right here. And then so on and so forth through the rest of them, and that creates now a paired data set between our observed value and the corresponding z value that goes along with the observed CDF of that particular data set. And through the magic of computers, then here is the plot on an arithmetic scale of our standard normal variant versus our number of cycles to failure. Here's all our paired coordinates in the blue dots, and a red line that's been fitted to that. Now, back in the old days, you would fit that red line just graphically. You weren't trying to milk this for too much. You were just trying to get a sense, best fit by eye. Hey, did this data look like it was approximately normally distributed? Was that an appropriate model to use? Right, well, it turns out that we can milk this for a little bit more, and there's a couple of features that we can draw out of this. We're going to learn way back late in the semester, about module 12 or so, how to come up formally with the linear regression line. That's what you see right here, is a linear regression line of this paired data. And note, it's just equation of mx plus b. There's your intercept value. There you go. And it has a particularly shallow slope. We'll talk about what that slope might mean. You'll also see a correlation coefficient, r squared, that shows up. And that tells us, being so close to 1, that our data very much is fitting a linear type of relationship. That's key critical kinds of information that we'll get into detail about. Where does that come from? Why does it really tell me exactly what I've just said that it does? Although we've seen that a little bit back in the covariance section of the previous module, module 4 that is. Okay, so that's correlation coefficient squared. Okay. Now note something here, that oftentimes what you're going to see in this data is very much what we see here, the beginning of the data to fall off away from that line, and it tends to like to fall off downwards, and then it kind of tends to go up a little bit at the other end, or vice versa. You see that quite a bit. What's interesting to me is how this data point out here is clearly swinging the line that we're fitting here. Right? As a potential outlier, well, that has some potentially undue influence. Although in this case, it really swings that line, but look at what happens to the main body of the data. That does pretty well through there. Right? So that's kind of interesting that it has the appearance of having such a significant influence, but really it doesn't. It just so happens to be fitting right along with the rest of the body. It's really these that are starting to fall off a little bit. And again, the linear regression segment of the course, we'll get into more detail about what that potential influence really is. Right. But it is key to note that this still might be a potential outlier. When we looked at this from the box plot, that said, well, no, not really. The box plot version of this said, we don't think that is. And that might very well be the case. If we collect more data beyond 70, get 700, say, so a whole order of magnitude more, maybe we fill this in and we fit back along this line. Or we may find out that as we collect more and more data, that this particular model, which looks pretty good right now, turns out to not necessarily be that good. For instance, the Weibull model is oftentimes used in fatigue or cyclic kinds of models, or tensile strength models, and there's some particularly important reasons why. Okay, and we're not seeing that in this particular data set, and that's an interesting question then of, well, why not? Why is it that the Weibull, or a different kind of model, is so good, but yet this one looks pretty darn good from what we see here? And we're going to get into those kinds of questions as we move on later in the semester.